So thank you, Gianluca, and I'd like to start off by thanking the conference organizers for asking me to talk about this topic. It's really a real pleasure to be here. I always love being at Santa Barbara, and it's been a really great conference so far. I'd also like to thank, so a lot of the work, and the last part of the talk today is going to refer to work done by the T-Dino collaboration, and there's many people, I can't thank them all by name, but I'd particularly like to thank Charlotte Palmer, Hannah Paul, Don Lam, Pedro Safrakos, and Gianluca for their hard work and extensive involvement in this collaboration over the years. So my talk's going to have a kind of three-part structure. I'm going to start off by giving a kind of brief review of a kind of general and theoretical understanding of plasma turbulence. Given the time, this is going to be incredibly incomplete, and I'm perhaps even biased, just focused on some things that I'm particularly interested in right now. And then I'm going to, particular theoretical difficulties in comparing, say, classical pictures of plasma turbulence versus classical turbulence versus plasma turbulence. I'm then going to talk about experiments investigating astrophysically relevant plasma turbulence, and then finally, maybe in the spirit of this whole conference, talk about future opportunities for new experiments, both on the current generation of facilities and the next generation laser facilities. So now a wealth of astronomical observations have shown us that plasmas in various different astrophysical contexts are turbulent. This includes the solar winds, black hole accretion flows, and the intracluster medium of galaxy clusters, and there are many other astrophysical plasmas besides. And this kind of observation matters because if plasma turbulence is there, it really affects key astrophysical processes such as magnetogenesis, as we've just heard in James's talk, plasma heating, and then cosmic ray acceleration and transport. So how do astrophysical plasmas that we typically find compare to plasmas encountered in more terrestrial environments? Well, I think probably the key three features are that astrophysical plasmas tend to be much hotter, lower density, and magnetized. And this tends to have the consequence that the constituents, particles composing those plasmas have a Larmor radii that are much smaller than both the macroscopic length scales over which density and temperature vary, and also the Coulomb mean free paths between of those particles. So if we take those three plasma environments that I just mentioned, the intercluster medium at the Bondi radius, at the Coulomb radius, a Sagittarius A star at the Bondi radius, and the solar wind at 1 AU, and then we take astronomical observations to estimate densities, temperatures, and magnetic field strengths, we can then compute both the Coulomb mean free paths of particles and also their Larmor radii. And you can see that for all of these three systems, there's a characteristic hierarchy. The Coulomb mean free paths are comparable to or smaller than the macroscopic length scales, but then these Larmor radii are many orders of magnitude smaller. These environments aren't all the same. You can see that the intracluster medium is better thought of as being weakly collisional. Collisions do place some constraints on the distribution function, for example, whereas the solar wind is effectively quasi-collisionless. Another point that James made in his talk is because these plasmas are very hot, typically the magnetic Reynolds numbers in these systems are very, very large. Kind of naive estimates suggest as large as 10 to the 29 for the ICM, for example. Why do astrophysical plasma turbulence, such as these ones I mentioned, become turbulent? Well, this is actually a slightly non-trivial question because classical transport models of estimates of viscosity and thermal conductivity would, if you naively applied them to such systems, these weakly collisional and collisionless plasmas, would suggest that actually they wouldn't really be turbulent. The way you can look at this is if you take the estimates of the parallel viscosity and the parallel conductivity, and then from this estimate the fluid Reynolds number and Peclet numbers, you find that both of these numbers are perhaps a few orders of magnitude larger than unity or unity, which is clearly the opposite condition for very large fluid Reynolds numbers, which is what is required for turbulence. However, these models are in clear contradiction with observations, so there are too many to mention all of them, but one I wanted to highlight was some work done recently by Irina Zurab-Lever at the University of Chicago, and so by looking at X-ray emission fluctuations of the Coma cluster, she showed that effectively the spectrum of these fluctuations extended well below the scale you'd expect if classical models of viscosity were to apply to such a plasma, and indeed you have effectively some type of, the turbulent spectrum that she observed is roughly compatible with a Kolmogorov turbulence in a high Reynolds number fluid. On on terms of the Peckley number, so these are observations of the Perseus cluster, and again, by looking at X-ray surface brightness emissions at different energies, Eugene Tarasov was able to back out these kind of temperature maps of the plasma, and you can see that there were the temperature fluctuations on very small scales, again, inconsistent with a Peckley number that's of order unity. So what's going on here? How do we reconcile these observations with the sort of classical theories? Well, the answer is that actually astrophysical plasmas tend to have a much more complicated interplay between their macroscopic scales and the microphysical response, fundamentally a changing transport. So probably the most well-known and simplest example of this is the relationship between pressure anisotropy generated by macroscopic evolution and microinstabilities. It's well known, and actually was mentioned at a talk yesterday, that if you're in a magnetized collisionist plasma, pressure forces act anisotropically with respect to any background magnetic field. So if one was to consider a model without heat fluxes, you can deduce the so-called Schugerberger-Low equations that are basically conservation equations for the perpendicular and parallel pressures. These have a simple physical interpretation. The conservation of perpendicular pressure corresponds to the conservation of the first adiabatic invariant, or the mu invariance, whilst the conservation of parallel pressure is related to the conservation of the so-called bounce invariant, particles trapped in magnetic mirrors. And you can see from this that because parallel and perpendicular pressures under the Schugerberger-Low equations evolve differently as the magnetic field and density evolves, as a plasma evolves macroscopically, you'll naturally develop pressure anisotropy, the differences between the parallel and perpendicular pressures. Why does this matter? Well, it's well known and now very well established that plasmas with very small, even small pressure anisotropies can become generically unstable to a whole zoo of different microinstabilities once pressure anisotropies become sufficiently large. One example of these instabilities, probably one of the earliest discovered, is the so-called fire hose instability. This is if you have some alphanic perturbation. If the pressure anisotropy becomes sufficiently negative, parallel pressure forces can overwhelm restoring alphanic forces, and so an alphanic perturbation such as, or a flux tube like this shown here, can actually, if it's perturbed, will actually grow in amplitude. Well, there have been, particularly the last few decades, quite a number of both analytical and now numerical studies of the properties of weakly collisional and collisionist plasmas exploring this complicated interplay. And I think it's actually fair to say that now has been very significant progress in understanding what's going on here. So in terms of the microphysics, we now know that these instabilities typically give rise to anomalous collisionality, and it can also give rise to anomalous particle populations, for example, groups of particles which are trapped and then others can stream around the plasma, some other ones cannot. So, for example, these were simulations done nearly a decade ago now by Matt Kuntz, who was looking at the fire hose instability in a shearing plasma, and he showed that, so we got fire hose fluctuations developing, and he then confirmed that these fluctuations in a saturated state do give rise to quite a significant anomalous collisionality. We now know more about the thermodynamics of these weakly collisional or collisionist plasmas. For example, we now know that the instabilities generated by pressure anisotropy typically regulate that anisotropy growth and can also give rise to anomalous heating. So this was work, for example, done by Lorenzo 10 years ago, looking at a compressing plasma. And in this case, the ion cyclotron instability regulated the both electron and ion pressure anisotropies, shown with the blue and red curves respectively. And also in this particular case, the electrons were heated anomalously compared to adiabatic predictions by the interaction of their modes with the ion cyclotron modes. Waves, even basic plasma waves in the system, behave quite differently to just a collisional plasma. For example, John O'Squire did a study nearly a decade ago showing that if you have a shear alphane wave, actually the pressure anisotropy caused by the wave actually generates instabilities that then cause that wave just to be damped. So what you're looking at here is the magnetic field evolution as a function of time. You have some initial wave, but then you can see fire hose fluctuations generated by the wave, and then the wave just damps without propagating. And finally, there's very interesting work that's been done looking at the interrelationship in these plasmas with non-thermal particle populations. It's been shown that, for example, instabilities can actually generate superthermal particle populations. And I just wanted to highlight some very recent work done by Patrick Reichertzer at the University of Oxford, where he actually showed that, for example, in some circumstances, these microinstabilities can actually dominate or be the dominant process for affecting cosmic ray transport. So in particular, this is, Patrick looked at simulations of the mirror instability and showed that if you propagated high-energy particles through this, that actually for probably GeV to TeV cosmic rays in the ICM, the kind of modifications to transport due to these microinstabilities dominated the transport of those cosmic rays. So what are the implications of all of these? We now understand weakly collisional collisionless plasmas a lot better than we did before. What are the implications for plasma turbulence? Well, it's a bit of a mixed picture. Sometimes we find that astrophysical turbulence actually does behave like conventional collisional MHD models, but sometimes it doesn't. So one example of where there actually is a lot of similarity was some work I did a few years ago when I was at Princeton looking at strong alphanic turbulence in an expanding plasma. And in an expanding plasma, this is inducing increasing negative anisotropy, so one might expect that this could generate instabilities and, in fact, destabilize or interrupt the whole cascade. However, that's not what happens at all. Actually, it turns out as the turbulence expands, you do generate instabilities, but they simply just regulate the anisotropy, and the overall kind of Goldreich-Schroeder picture of our strong alphanic turbulence still holds with just a few kind of quantitative changes rather than anything qualitative. However, this is not always the case. A few years ago, John O'Squire discovered the phenomenon of magnetomutability. This is a phenomenon whereby in weakly collision or collisionless plasmas, fluctuations that don't change the magnetic field strength are preferentially selected in some sense over those that do, because the ones that do often are very strongly damped by instabilities. And so, for example, John, believe it or not, you can actually have a cascade of these magneto-immutable modes, and so this tends to kind of preference one type of plasma mode over another that you wouldn't see this difference if you were in a collisional plasma. And finally, some work that some hybrid kinetic simulations that Lev Azamasky did looking at high beta alpha weakly collisionless turbulence found that actually instabilities can create these kind of non-local relationships between large scales and small scales, inducing anomalous viscous scales and also spectral slopes that don't behave anything like the kind of conventional hydro picture. So in short, there is this, we now understand a lot more about plasma turbulence, but basically plasma turbulence shouldn't be conceived of as being just like collisional MHD. There are these quite subtle relationships that can arise due to instabilities usually. Okay, so I've given a kind of very brief review of our understanding of the kind of state of play theoretically. What about experiments on astrophysically relevant plasma? So it has actually been possible over the last few decades to explore the physics of weakly collisional and collisionless plasmas in the laboratory, but there are various limitations on the different ways of doing this. So probably the prima facie measurements have been done in the solar wind by spacecraft. So for example, this is one of the most famous measurements, the so-called Brazil plot, showing the regulation of parallel and perpendicular temperatures by the fire hose and mirror thresholds. And the strength of these measurements is that you can get comprehensive measurements of fields, particle distribution functions, and there already exists a massive wealth of data from the various missions that have been done over the last decades. However, the challenge is that you have very little control over what conditions the probe sees. The sun will just spit out whatever plasma it's going to do. And also, and because this is a very particular environment, there are questions about how generalizable these results are. In the lab on Earth, there are various experiments that have been done. So, for example, there are experiments done on the large plasma device looking at weakly collisional plasmas. So these were some experiments done a few years ago looking at the properties of electromagnetic magnetic drift waves. And so they found this quite nice observation that as the plasma beta in this system changed from being very small to quite small, you get a dramatic change in the kind of the eigenvalue morphology of these waves. And this really is a genuine collisionless plasma that you can explore and characterize very well. However, this is effectively a magnetically confined plasma, and so accessing this, you can only look at a limited space. These kind of low beta plasmas, looking at higher beta plasmas is not possible in this particular setup. Recently, the Big Red Ball at the Wisconsin Plasma Physics Laboratory came online. This is a device where it confines a plasma with kind of lots of magnets around the edge of it and can, by puffing in bursts of plasma, create high beta plasmas in the lab. This was a demonstration experiment that they reported a few years ago, showing that they can indeed access both high magnetizations of ions, the blue line, and high betas, the red and green lines here, simultaneously. However, the downside of this setup is that it's very hard to get large-scale separations. Those ion gyroradii are typically only an order of magnitude smaller than the device size itself. And so to get realistic scale separations will be a real challenge in this sort of device. And then finally, there were the sort of laser experiments carried out on the very highest energy lasers, Omega and NIF, that Derek mentioned yesterday. So, for example, this was an experiment led by Jenna Meinecker, done on the National Ignition Facility, which created a weakly collisional plasma in the lab and showed that actually thermal conduction in that plasma was strongly suppressed. So if you had classical conduction models, a simulation, you get kind of maps of temperature that look like the top, but in fact the actual data had a lot more structure in it, and this was consistent with a suppression of conduction by a factor of a few orders of magnitude. So the strength of this is that you can naturally create high beta magnetized weakly collisional plasmas in the lab very easily. However, these facilities, you don't tend to have that many shots, so getting really good quality statistics is a real challenge. And also, the collisionality tends to play a much correspondingly more important role here than is done in astrophysical applications. So, what about studying astrophysical relevant plasma turbulence in the lab? What can we do? Well, I thought I would focus on the work of the T-Dyno collaboration, which I've been involved with since I started in this field, started by Gianluca Gregori over a decade ago now. And in particular, this is looking at work that's very relevant to what James was talking about, the phenomenon of magnetic field amplification in turbulent plasmas. So the first experiments were done on the Vulcan laser over a decade ago now. And so the way these experiments work is you put laser beams onto a target. So in this case, it was 2 rods. That creates jets of plasma. Those jets then pass through grids, and like water flowing through a grid, the grids effectively induce turbulent motions. And then on the collision, you end up with a turbulent mess of a plasma, which is exactly what we want. And so this is an optical image illustrating what one of the experiments looked like on that experiment. And so what, the kind of key finding of these initial experiments was the creation of these turbulent plasmas in the lab. These plasmas had magnetic Reynolds numbers that were somewhat larger than unity, though not hugely so, and amplification of the magnetic fields were indeed observed. However, as James pointed out, there's an onset threshold for true dynamo action, the ability of a magnetic field to be amplified up to dynamically significant values. And so basically the experiments here weren't done with enough laser energy to get to those hot enough plasmas for that to happen. So what happened next is we then went to the Omega 60 laser and did experiments using 5 kilojoules of laser energy per target rather than 300 joules. So again, you have the laser beams from Omega coming either side. That creates, of these 2 fours, that creates jets. Those jets then pass through the grids, and you create your turbulent plasma, which we then diagnose with actually a lot of the same diagnostics that Derek mentioned yesterday, Thomson scattering for measuring the plasma parameters, photon radiography for magnetic fields, and X-ray imaging to diagnose the turbulence. And the kind of key result was here is that we achieved about magnetic Reynolds numbers of maybe 400 in this experiment, and did indeed observe bona fide dynamo action. The magnetic fields that were amplified, there was this very significant energy amplification, and in their saturated state, the fields seemed to be dynamically significant. We then built upon this target to move to different types of dynamos. So James mentioned the importance of the magnetic Prandtl number for dynamo action. In particular, these first experiments were in the low Prandtl number regime, which is perhaps more relevant to, for example, planetary interiors. For plasma turbulence, we really want to move to larger Prandtl numbers. And so by adjusting the platform by, for example, changing the target materials, changing the laser pulse shape, and the grid design, we were actually able to create a turbulent plasma in the lab that had an order unity magnetic Prandtl number. So what you're looking at here is the schematic of the target we used in these experiments, and then here are 3 X-ray emission images of the plasma showing the development of the plasma turbulence. And then here are some maps of magnetic fields that we extracted from the proton radiography data, showing very strong amplification of the fields and the creation of stochasticity in those fields. We then followed up from this experiment and actually did something not too dissimilar to what James mentioned by introducing different seed fields and seeing how that affected the properties of the dynamo. I'll be pleased to say that these results are actually consistent with what James reported, in that when we introduced a large-scale seed field and then compared that to just the self-generated seed, which is much smaller, in the final state of these 2 dynamos, the turbulent fields are very similar. And the statistics of these fields and the characteristic strengths and so on were indistinguishable within the uncertainties of those measurements. So this actually supports exactly what the simulation results that James just reported. And then most recently, and relating back to what I was talking about earlier on, we we want to push to making astrophysically relevant plasmas, and so by going to the National Ignition Facility that has even more laser energy, now 133 kilojoules of laser energy, we can actually create weakly collisional plasmas where those electrons, certainly the electrons and possibly even the ions, are becoming microphysically magnetized. And I suppose the most interesting, so you can create a turbulent plasma, turbulence does indeed develop, and also magnetic fields, very, very strong magnetic fields develop in this setup. So this is effectively a beam of protons that's been injected through the turbulent plasma, and if there are no fields, they all just be sitting inside this slit, but they've been deflected all over the place, and that is consistent with mega-Gauss level magnetic fields. What's very interesting in this case was this plasma, in some sense, is the most efficient dynamo we've ever created in the lab. It's highest RM, highest magnetic to kinetic ratios reported, but it is also very much in the weakly collisional regime, suggesting that some of these issues about microphysics may not be so significant for the efficacy of dynamo action. What else can we do? We can actually now do lab studies of supersonic plasma turbulence as well as subsonic. All of those previous experiments had Mach numbers between maybe 0.2 and 0.5, but we can now actually access Mach numbers greater than unity. This was based on initial experiments done by Tom White on the Vulcan laser. So again, it's the same principle. You're colliding flows together, but you're changing the materials in order to access the supersonic regime and changing the pulse shape of the lasers to create faster velocities. Tom, with this work, managed to show quite nicely that when you move from being subsonic to supersonic, the spectral slopes of both the velocity spectrum, the density spectrum, diverge from each other from Kolmogorov to Burgers, and then a shallower spectrum for density, actually in a way that's very consistent with both observations and theoretical models. We then built on this and went to a larger laser than Vulcan, so these were experiments done on the laser megajoule in Bordeaux, France, and effectively we then used by tuning the pulse and made a turbulent aluminium plasma, and we then probed the magnetic fields in that using photoradiography, and indeed you can see the development of stochastic fields. The RM that we got in this plasma was about 50, and so we didn't really seem to observe full dynamo action. We observed magnetic field amplification, but the fields didn't become dynamically significant. We then did more experiments, then went to the omega-60 laser, and then changed our target again to try to get into an even higher RM and get into the supersonic plasma dynamo regime. So these are some probably our most recent results, and are very exciting. These seem to be consistent with the operation of a supersonic plasma dynamo. Again, it's the same sort of principle. You're firing laser beams at a target, creating a turbulent plasma, and by shaping the material, in this case we had chlorine dopants in this in the targets that tend to favor the creation of supersonic turbulence, and also have an enhanced laser pulse to get faster flows. And then, so Hannah Poole, who was led this experiment, so she this is Thomson scattering data, like Derek showed yesterday, collecting both the ion acoustic wave and electron plasma wave feature. And then by analyzing this data, she was able to determine what the turbulent Mach number was in these experiments. So you can see here that it's a time-dependent quantity, but we were able to get into Mach numbers peak Mach numbers of about 4 here. And then we can use the photoradiography to diagnose the evolution of the fields. And then, and indeed, you see stochastic fields developing, and these fields are also dynamically significant. So this shows that you can now in the lab do quite interesting experiments investigating a supersonic turbulence and dynamos. And finally, which I thought might be of interest to many of the people here, we can also do experiments looking at the relationships between plasma turbulence and high energy particles. So these days, either using high intensity lasers or particle accelerators, we can produce fast particle beams, even highly relativistic beams. And so it's possible to study their interaction with plasma turbulence. So one of the earliest experiments we did in this regard was led by Laura Chen, again on the omega-60 laser. We created effectively the same T-dyno plasma and then fired a beam of protons through that plasma, which we collimated using a pinhole. And then we looked at its diffusion and compared that to standard models of fast particle diffusion through a turbulent plasma and in intermittent fields. And we found that effectively that the data matched up very well with theoretical expectations. More recently still, we did some experiments on the GSI Darmstadt facility at Darmstadt, which has some kind of smaller lasers, but that is combined with a linear accelerator, the UNILAC, that can accelerate heavy ions. And what's particularly unique about this facility is you have a very, the initial spread of energies of the UNILAC beam is incredibly well characterized. So you can do very sensitive measurements looking at, even if acceleration is quite a weak process, you can actually see that acceleration in the lab. So in this experiment, we created a turbulent plasma by irradiating two foils that had kind of indentations on, and then on the collision of those two foils, effectively the fact that the indentations are misaligned meant that you end up with a turbulent flow in the center. We then fired the unilac beam straight through that, and then looked at how the energy changed as a function of the plasma conditions. So this is, for example, some experimental data showing, though this is interferometry data, so not high enough resolution to see the turbulence, but you can see the formation of a sheet of plasma in which there are turbulent fluctuations. And what was very interesting about these results is that we both spread of the beam and in some cases acceleration of the beam was observed at a rate that seems to be substantially higher than would be expected due to second-order Fermi acceleration if you just from the macroscopic turbulence that we believe is developing in this setup. So we believe that maybe there might be micro-instabilities going on that are actually causing an anomalous acceleration in this case, and so these were quite interesting results. So coming up, apologies. The whole thing has come off. I'll just hold it. So I just wanted to finish by talking about future opportunities and in the spirit of this conference and ask, how can we best leverage both current and then the next generation laser facilities to study astrophysically relevant plasma turbulence in the lab? Well, what we can now do, we can many facilities now have both kilojoule and even some megajoule capabilities, and this means that we can reliably create hot, tenuous, magnetized plasmas with plasma beta probably order unity or greater in the lab very easily. We can do lower beta plasmas with different facilities, for example, Z pinches. I will say that at the moment, to generate thermal plasmas that are relativistic, as might be of interest to many of you here, is likely beyond the capabilities of what this sort of energies are capable of. Basic energetics can tell you that. So if you want experiments on relativistic thermal plasmas, you may have to wait a few decades. However, what we do have is the now capability to create very high-intensity laser beams, and this means that we can create these energetic particle beams, including relativistic beams, which is great for both experiments and also diagnostics. Thank you. Therefore, this suggests that whilst we may not be able to create relativistic turbulent plasmas in the lab easily, we can look at, for example, the interaction of beams with non-relativistic turbulence. And so if you have a particular astrophysical environment in which, and you want to do experiments investigating those sorts of interrelationships, we now can do experiments in the lab looking at that. Some facilities that are coming online, for example, the Apollon laser, now have the ability to do a much higher shot rep rates than a previous, say, Omega or NIF. And this means that we might be able to get really high-quality statistics and then look at quite a kind of more precise effects than has been possible in the past due to getting much smaller errors on things. So those are some of the opportunities. What's the challenges? Well, the first one is actually creating plasmas that are genuinely astrophysically relevant. One of the ones that I mentioned earlier is how you create plasmas where there's the sort of large-scale separations that you have between these microphysical kind of plasma scales, these Larmor scales, particularly of ions, and the macroscopic scales. That still remains a challenge to create large-scale separations in the lab. There's also this, as I've mentioned, generating these thermal relativistic plasmas is a severe challenge, but actually generating even kind of GeV electron beams using the current day high-intensity beams is much easier. Another question, particularly then thinking about the high rep rate experiments, there's a question of targetry. How do we mass produce these such complex targets that would be required for turbulence experiments? And there's also the question of diagnostics. How do we implement this reliably at high rep rate? Doing photon imaging, for example, at high rep rate is something that requires a lot of theoretical work. So to conclude, and I just thought, because I realized just before this that I didn't have any AI in this talk, and given it's 2025, that's very out of date. I just thought I'd throw on, this is what ChatGPT 5 thinks astrophysical plasma turbulence looks like. But yes, so to come to my conclusions, plasma turbulence is ubiquitous in many different astrophysical contexts, the solar wind, black hole accretion flows in the ICM, and it's thought to play a key role in various processes, magnetogenesis, acceleration and transport of cosmic rays, and heating, and also interpretation of observations. The key properties of these plasmas, which are typically weakly magnetized and with a low Coulomb collisionality, remain uncertain, but there has been significant progress recently. And I guess the key takeaway is that whilst there has been a lot of progress made with analytical studies and numerical studies in previous experiments, we can And as I've shown you, we've learned a lot about plasma turbulence in experiments. The next generation of laser plasma experiments should be able to provide a really key approach for actually testing theories. But I think to do this well, we need to have a discussion with genuine astrophysicists to really make sure that we're identifying the most promising areas. So with that, thank you very much for your attention.
Thank you, Archie. So any questions? Yeah.
Thank you. Thank you very much, Archie, for a very insightful and stimulating talk. All right. I have a couple of questions. Yes. Right. One is on your laser plasma experiments. You showed many experiments, but I wanted to get a better sense of the physical regimes that they are in. In particular, are they, to what degree are they collisional or collisionless?
Yeah.
When you insert a grid, right, that grid controls essentially the injection scale, right, of your energy.
Yes.
What is the mean free path compared to that scale? For electrons, for ions?
So to answer that question, so for the dynamo experiments I showed you actually on both omega and NIF, so the lowest energy experiments are very, very collisional, and so those aren't really the astrophysically relevant regimes. Your mean free path is 4 or 5 orders of magnitude smaller than the grid scale. But then as you move to the higher energy facilities, omega and NIF, the collisionality is going effectively down to the point where the NIF experiments, the mean free path is still probably, it's ICM-ish like conditions in the sense of your Coulomb mean free path is maybe 2 orders of magnitude smaller than that grid scale of ions and electrons. But the crucial thing is for electrons...
The grid spacing, right?
Sorry?
Then the grid spacing, not the whole...
The grid spacing, specifically. So your mean free path is maybe 3 microns, your grid spacing is 400 microns. So there's about 2 orders of magnitude there. And then what's on NIF, you're getting to strong enough fields so that actually now the electron Lama radii in this experiment are nearly an order of magnitude smaller than that. So microphysically, these plasmas are getting closer to what's possible in the lab. The one thing we've not managed to do yet, and even on NIF, is get to the point when the ions are microphysically magnetized. Those ions should basically still be conceptualized as being unmagnetized collisional ions. But hopefully, with more refinements, and we have some ideas about how you might be able to get to a genuinely collisionless plasma or weakly collisional, where all of your particles, both ions and electrons, are genuinely magnetized microphysically.
Thank you. The second question is, you talked a lot about lasers, but there are other machines, in particular like the Z machine, for example, pulsed power. What are your thoughts on that?
This was a sensor biased review of experiments because I've worked myself on the laser experiments. So the Z machines, as we saw yesterday, for example, with Derek's talk, there's a lot of interesting research that can be done on looking at this is relevant to astrophysics. I think the same is true for turbulence as well. There's been some work on this done on MAGPIE. The key difference is it's a different regime. So that if you want to look at MAGPIE and its Z-pinches typically generates beta order unity or lower beta conditions. And so if you were interested in strongly magnetized turbulence in that sense, then you can access that regime on those facilities. So laser experiments are good for higher beta, Z-pinch is better for lower beta.
Thank you, question from Lorenzo?
Great talk. I still have a question on the NIF experiment, maybe like a clarification mostly. So can you comment on like turbulent dynamo versus, say, a magnetogenesis process that just makes field?
Yes, so in these experiments, the seed field itself is generated by the Biermann battery operating at the laser spots, and then that's advected in with the flows into the turbulent plasma in the center. However, that seed field is much, much more weaker. And then what we see, and it's also ordered, so it's this mechanism that it's actually often used for reconnection experiments with lasers, where you basically get an azimuthal field. But then what you see is that the development of a stronger, much smaller scale field.
There's another question there.
I was just wondering, in the MMS data and in my simulations, as I showed, we're seeing so much alignment between all the primitive variables and its curls. Is there any ability to measure kind of current helicity, magnetic helicity, cross helicity in these experiments?
The trouble is
the structure is preserved, by the way, through the columns. So you integrate these and you do still preserve the fluctuating helicity.
Interesting. So we should have a chat and work out this, because most of your measurements, with one exception I'll come to, have to be path integrated. So sometimes this actually, for example, if you want to say measure intermittency of magnetic fields, can be a challenge, because even if you have intermittent fields, if you average along a path, everything starts looking more Gaussian by the central limit theorem.
Yes.
But if it can be preserved...
It is preserved through the path.
Yes, so that's very good to hear. There's also, so Thompson scattering is a diagnostic. This is capable of doing point-wise measurements. And so John Newcomb and I think that in the right conditions, you might actually be able to measure magnetic fields locally using that technique. So that might be another way of actually, you can then, and what's nice, you simultaneously get the velocity and the magnetic field in the location, and so you could look at alignment quite easily.
Fantastic. And I just want to say, I think my simulations look better than what GPT-5 can produce. So
yes, I think I agree.
This is good.
Well, so I was a bit depressed by this, actually. So I gave a talk like this a few years ago, which I used GPT-4, which is on the left. And then I don't actually think GPT-5 is that much of an improvement, which seems to be the general consensus as well.
So maybe to add to your answer, Archie, is that in some, for example, remember in the Omega experiments, we actually measure magnetic field spectrum, which is not Gaussian.
Yes, no, that is true.
So that is possible.
Yes, yes.
Appreciate the chairs all running around the room. So Archie, just to follow up on what Lorenzo was asking, actually, because I'm completely 100% ignorant on experiments whatsoever. But would it be possible to then design an experiment where you let the magnetogenesis create the seed fields for you? As in, in numerical experiments, this is done by adding an external force, a body force to the particles that then, with kinetic processes, will make the seed fields for you. I have absolutely no clue if this is possible in an experiment, but do you have any thoughts on it?
Well, so the seed fields are generated by a physical process, the Biermann battery. So this is not something we've imposed on the system, they're just spontaneously arising, and then it's the turbulence itself then takes those seed fields and amplifies them. It remains to be seen as to, it would depend on the system as to whether, because the Biermann battery tends to operate much more strongly in laser experiments than it does in astrophysical contexts. So whether or not the exact seed fields mechanism is going to be the same between these two cases is probably not, but we'd have to chat about it to work out in a particular context.
Thanks. I was kind of following up on what Dimitri was going to ask. Yeah. Can you just talk about exactly what determines the collisionality? You were talking about like the energy, but then there was something about a grid. So like, why is setting the collisional mean free path hard? How much control do you have over it by changing material, et cetera?
Yes, so basically what sets that is, collisional mean free path scales very strongly with temperature, so the hotter your plasma, the less collisional it is, and also density. So one easy way you can get to a less collisional regime is just more laser energy, because your resulting plasma is hotter. However, it's not entirely trivial. The interplay it's not quite as simple as that, because often if you fire more energy onto a target, you may get more density out. But generically, you can kind of by tuning the target material and tuning the laser energy and also the pulse shape, you can have some control. The distance also makes a difference. Yes, that's another thing you can control. There are two targets. So we have gliding jets, and if you have a wider separation, typically that reduces the density. The other big thing you can change is whether you use a rear side blow-off plasma, which is what we're using. So that's when you fire a laser at a target and then you get a jet out the other side. They tend to be colder and denser. Whereas if you use a front side blow-off plasma, which is the plume emitted from the same side the laser is coming from, they typically are much lower density, hotter, and stream away faster. The issue for counter-streaming experiments, if you try and then collide those two, actually often typically those plasmas will just stream through each other, and then you get very interesting physics, you get vibrant stabilities, but this is not the turbulent dynamo in the sense that we wanted. But in principle, one of the things looking forward, I think if you wanted to access a more collisionless regime, thinking about using front side blow-off plasmas for these sorts of experiments, but working out how to avoid Weibull type instabilities is definitely a promising way forward, I would say.
Any more questions? Yeah. Oh.
Thank you. I'm just wondering how well you can actually resolve the nonlinear regime in these dynamo experiments?
Good question. So at the moment, so we actually in some ways have an analogous problem to what you were discussing. So we can't resolve resistive scale fields.
Yes.
What we can look at is effectively it's like observations. You can look at the nonlinear evolution and get the spectrum. And actually this is actually, I think, one of the values of actually doing experiments is so we had quite an unexpected finding for one of our Omega experiments, which was the scale of the field we observed was actually larger than our simulations predicted. So it seemed that the actual plasma that we had was more efficient at generating large-scale field than, we still haven't quite actually got to the bottom of. We have a few theories as to what's going on, but we haven't actually pinned down one mechanism explaining that yet.
What we're trying to understand right now is that the nonlinear stage in the supersonic dynamo actually grows quadratically, and the nonlinear stage in the subsonic dynamo grows linearly. So this would be something.
Yeah, so
that could potentially...
in principle, that's an experiment you could do. So the nonlinear phase you can resolve that in time. So we've done time-resolved measurements of dynamo. You could, in principle, do a supersonic and a subsonic experiment and try and compare that in the lab. I think that's feasible.
Okay, cool. Thanks.
Okay, any more questions? Okay, so maybe last question is, what do you think is the next priorities for this type of experiments?
Well, so I actually think that going to these, pushing more towards weakly collisional and collisionless environments is one of the highest priorities. I also think looking at environments, things that are very hard to simulate. So, for example, this intermediate collisionality regime is actually very challenging to simulate and get turbulence. And so actually experiments have a real value there because it's very hard to actually come up with a simulation that works well. So I think those are two things that I would be interested in.
Very well. I think it's time for a coffee now. So let's thank our speaker.
Thank you.
And then we meet again at 11 o'clock.